Now, here we will start a series of lectures that will establish the formation of baryonic structure. So basically what we will do in this series is that with some introduction we will first talk about the linear perturbations in baryons. Then we will talk about the nonlinear collapse of baryons. Right? Then we will discuss the mass functions and abundances. Okay, the abundances of baryons, we mean. Then we will talk about the angular momentum of galaxies, galaxy formation and evolution. Galaxy distributions in projection. With with some hints on magnetic fields in the universe. So these are the 7 topics that we will discuss in this series of lectures. So this formation of baryon structure. Now, so we have already studied the formation of the structure of the universe, and this baryonic structure is very much similar to those reactions. Now here, say that there is some fundamental physical consideration, and that is there is a wide variety of physical processes here that we need to take into account. Now these galaxies by themselves show a variety of morphological and physical properties. Right? So morphological and physical properties. Physical properties. Now these morphological means that the properties that are important for the formation of the structure, and the physical properties describe the the fundamental properties. The physical properties are the fundamental properties that are I think that we have to write bigger. Physical properties describe the very properties of the galaxies themselves. So now here we are studying, we have studied the formation of structure of galaxies. This we have already done. Now we are studying the formation of the baryonic structures. So here by these properties we would mean the morphological and physical properties of these baryonic structures. Okay, now we know that at this Z, like this is the Z a number. This is the redshift number. Now this formation process, it should be such that there are relatively structureless conditions, right? Relatively structureless conditions at high redshift. It's more or less 25. The density enhancements at this redshift level are describes the relatively structureless condition of the baryonic structures, baryonic elements. Now, what are the difficulties? The results are very unsatisfactory. Why is that so? Because simply we do not have enough samples. Okay? Not enough samples. And often we have to decide that how to make the correspondence between the sources. Like there are some sources that are seen in high redshift. Okay? High redshift. There are some sources which are seen on low redshifts. How do we make a correspondence of this? It is still unsure. We are still unsure. So this is a very the issue, and this is further complicated with the fact that certain kind of population, like say you are studying at T equal to T1, certain kind of populations are there, they are not there at T equal to T2. So they vanished outside this epoch. So we, how do we handle that? We create a kind of conjecture that invoke new population in this epoch, but that is also not very satisfactory. Okay, so this is the problem number 2. This is the problem number 1. This is the problem number 2. So these are the problems that are there. Now, a problem number 3 is that the galaxy formation, like the galaxy formation, there are different kinds of scenarios that you already know. We have studied these in this, the scenarios in the formation of the structure of galaxies. So these scenarios of formation of galaxy. These are very much tied up with other redshift phenomena. Tied up with other redshift phenomena. Right. Say for example the AGN, existence of AGN. Then you have a fourth problem. What is that? That is that now this galaxy formation scenario, it must fit with a broader picture at different scales. So when you say broader picture, that means this is the large structure of the universe. When you study the large structure of the universe, that broader picture scenario must fit in the broader picture. Say we talk about the pattern of density inhomogeneities. We have studied these density inhomogeneities before, and say the density inhomogeneities at very high redshift. Say for example, Z is Z on 10,000, 1,000. Where do we get these things? This we can infer from the CMBR anisotropies. Right? This kind of density inhomogeneities we can infer from CMBR anisotropies. This we can use as the initial condition for the growth of perturbations. Now all these things we have studied in detail while we were studying the formation of the structure of galaxies. Okay. So growth of basically what I'm saying this again just to relate these lecture to the formation of the structure of galaxies, because on formation of baryonic structure we will be very much indebted to this. We will derive much of our equations and solutions from here to here. Okay. So this growth of perturbations, while studying this growth of perturbations, we have to take these things as the initial conditions. Okay, the density inhomogeneities. Then we have a fifth problem. What is that? That a visible part of the galaxy made of stars, right? And the formation of these galaxies is essentially a study of cosmic star formation. Okay? So these galaxies are made of stars. Made up of stars, right? So the formation is essentially study of star formation as well. Okay. Now what happens is that when the star forms, star formation, they leak out radiation. And these radiations, these leaked out radiations, we can detect it. And various waves, like say radio waves, microwaves, infrared, right? Even gamma rays. So we can detect these leaked out radiations. And also one very important thing is that evolution of metallicity. Evolution of metallicity. This is extremely important. So this evolution of metallicity, if we study this evolution, the history is embedded within this. Within such evolution. Right? So now these galaxy formation scenarios. These galaxy formation scenarios they must be consistent with this evolution. This evolution of this metals. And finally, we have a sixth problem, which are the galaxy surveys. So galaxy surveys we can perform in local universe. So we can perform otherwise, but if we perform this in the local universe, then it allows us to determine statistical parameters. All these things that we have covered before. Statistical parameters. What kind of parameters? Say, for example, the 2-point correlation function. 2-point correlation function. Of galaxies. Right. So, in the subsequent lectures that we have already talked about, like say the linear perturbations in baryons, the nonlinear collapse of baryons, right? All these things that we have talked about, we will actually try to address several of such questions, right? And we will start with the linear perturbations in baryons.